chút. Các em có muốn nghe thầy kể một câu chuyện
Ngon.
vui lắm.
Thầy chưa kể gì ạ?
Học thì sáng thứ 2 đầu sáng kia thầy có một hội nghị. Trong buổi này thì thầy báo cáo cái hội nghị mà nó mời là hội nghị ở bên tổ chức bên trường nước ngoài. Quen biết hội trường tạo cái thư viện Tạ Quang Biểu nó trên tầng 7 thì sau khi mà hội nghị nghỉ giải ra thì cũng có thời gian thầy đi làm một chút xem cái khoa học thế nào đúng không? Thì ở trên tầng 7 có mấy cái lớp học, một lớp độ khoảng 30 người nó thực hành là khoa của khoa nhiệt, khoa nhiệt hay là nhiệt lạnh hay gì đấy. Các em biết khoa đấy không? Các em biết là thầy nhìn thấy cái gì ở đấy không? Khi mà thầy nhìn vào trong lớp thầy nhìn rất là lâu, quan sát rất là lâu. Tại sao thầy quan sát ở lớp đấy? Tại vì trước đấy chiều ngày thứ 5 tuần trước thầy có một cái việc nên phải sang viện công nghệ môi trường ở cái nhà A30 ấy. Thì bên khoa công nghệ thông tin có cái phòng học ở cái hội trường tầng 1 nhà A30. Thầy chụp một cái ảnh, nhưng tôi thầy không share. Thầy giáo là một người Pháp đang dạy, đang giảng bài rất là say sưa trên giảng. Có độ khoảng 3 lần đầu tiên thì nó nghe rất là chăm chú, và phần còn lại là gì thầy chụp ảnh được. Có một trường hợp rất là đặc biệt, nó ngồi ngay lần đầu nó không nghe, nó đang chơi điện tử rất chăm chú. Một cậu bên cạnh thì nó đang đeo 2 tai nghe, nó không chơi điện tử, thầy không nhìn thấy màn hình của nó, nhưng mà nó đeo 2 tai nghe. Và khoảng 4 năm, tại vì lớp ICT nó đông lắm, khoảng 4 năm cái hàng cuối cùng đó, thì thầy nói thì kệ thầy em cứ cúi vào điện thoại. Thầy đứng khoảng 15 phút, thầy lấy photo, chụp rất là photo gửi cho các thầy cô trong ban giám hiệu. Chúng nó không nhận ra. Sau đấy một lúc thì có một bàn cuối cùng nhận ra, thanh niên lớn rất quen mình, nhận ra là mình đang chụp ảnh đó. Nhìn cái ánh mắt nó khó chịu. Nhưng mà không vấn đề gì tiếp tục. Thế nhưng mà thực sự là sau đấy là về mất một cái cuối tuần rất là buồn. Bởi vì sinh viên, giảng viên từ Pháp sang đây dạy, đúng không? Các bạn là trường quốc tế, giảng viên từ Pháp sang đây dạy, nhưng mà các bạn không biết đâu. Thế rồi đến lúc trước thì bảo là đề khó, các thầy cô ra đề khó. Rất là buồn. Có vẻ là chúng ta còn rất là xa để trở thành một trường quốc tế thật sự. Vì trường quốc tế thì cũng theo giảng viên trình độ quốc tế, và sinh viên thì trình độ quốc tế, sinh viên phải có cái cách làm việc của sinh viên quốc tế. Khá là buồn. Cho đến sáng thứ 2 sang bên khoa, nhìn vào các lớp của bên khoa thì hết buồn. Biết tại sao? Tại sinh viên bên khoa nó cũng thế. Và mình còn sốc hơn, mình sốc hơn, mình gọi mời đồng nghiệp mình sao? Em đang dạy lớp thực hành lên lý thuyết. Lớp thực hành mà anh, chúng nó đang nối mạnh. Chúng nó đang nối mạnh trên điện thoại kia, nó nối kiểu gì em? Chúng kệ chúng con đội đấy nó trượt chắc đấy mà anh, quan tâm gì. Thế thì thực sự là mình về mình kể chuyện với các thầy trưa ngày hôm qua ăn cơm ở trên khoa, mình kể chuyện với các thầy chuyện đấy. Nhưng bây giờ tôi hết buồn rồi, thứ 5, thứ 6 tôi lại thấy buồn, cuối tuần hôm nay tôi hết buồn. Hỏi là sao thì sinh viên bên khoa có sinh viên đi lớp thế hát thôi. Sinh viên đi lớp thế hát giống sinh viên bên khoa hiểu dân nghĩa như thế. Thế là các thầy bảo ông Gato với cuộc vừa, ông Sân Si với cuộc vừa thôi, đúng không? Ông buồn bởi vì thấy sinh viên ông không để ý, nhưng mà khi ông thấy sinh viên bên khoa nó thế thì ông thấy happy, vừa phải thôi, đúng không? Nhưng mà thực ra thì sau mà mình thấy là hình như có thể đó là giữa thế hệ các thầy và giữa thế hệ các em có một cái miscommunication, có thể đang có một cái gọi là đứt gãy thế hệ, đúng không? Tức là các thầy buồn tại vì các thầy thấy là các em không tập trung vào bài giảng, đúng không? Nhưng mà có thể là các em cũng rất là buồn tại vì các em thấy là ông cứ giảng trong khi mình có tập trung đâu, đúng không? thì có thể là làm ơn giúp thầy cái. Và nếu như mà chỗ nào không hiểu, giơ tay Phong ơi cậu nói cái tôi rất hiểu được không? Nó kiểu khác đi, đúng không? Hay là Phong ơi cái này easy lắm, câu hết đi, nói chuyện khác không cụ thể đi đây. Hoặc là Phong ơi cái này khó lắm, đừng nói tớ không nghe đâu. Làm ơn feedback lại cho thầy, không liên kết với thầy. Tại vì thực ra thầy trò gặp nhau một tuần có 2 tiếng đồng hồ đúng không? Có bao nhiêu đâu. Rồi hết học kỳ là thi xong qua môn là có gặp lại nhau nữa đâu, đúng không? Trên đường đời xô đẩy sau này có thể gặp nhau tí, có sao đâu. Biết đâu sau này thầy đi xin tiền các bạn thì sao? Nên thầy cũng không mắng đâu, thầy biết chắc và sau này thế nào có đứa sẽ cho trưởng tiền, nên thầy không dám mắng thế nào cả. Mắng đúng cái đứa mình đi xin tiền thì chết, đúng không? Không, nhưng mà thầy nói thật, tại vì mình chỉ có thời gian rất là ngắn, làm ơn giúp thầy feedback lại, đúng không? Các em dùng điện thoại máy tính không vấn đề gì, thế nhưng mà mình chỉ có cách nhau 2 tiếng ấy, thì cố gắng làm việc cho nó hiệu quả. Nếu mà những cái chỗ nào mà các em thầy nói khó hiểu quá, hoặc là các bạn có thể có feedback, Phong ơi vì tiếng Anh của cậu nó có fan action khó nghe lắm, nói từ từ thôi, ok không được, ok. Hoặc là Phong ơi đoạn này cậu nói như là tiếng Anh ấn bố em nghe được, ok không được. Hoặc là cái concept này nó khó quá, cậu thử nói tiếng Việt một tí có được không? No problem, đúng không? Thế nhưng mà đừng để nó trôi qua, tại vì 2 tiếng nó rất là nhanh. Đó. Mà thầy nói rồi, thầy lo, thầy buồn không phải là vì nó trượt môn của mình. Nó trượt thì cùng lắm, cô Thanh hiệu trưởng của Phong ơi sao để lớp trượt nhiều thế là cùng, đúng không? Thế nhưng mà cái mà thầy lo thật sự là các bạn sau 3 năm ở đây này, các bạn phải ra compete với cái độ nó hổ báo hơn rất là nhiều. Đội sinh viên ở các trường như là Singapore, xung quanh đây có Thái Lan, đúng không? Mà các bạn biết rồi, có bạn nắm được tình hình là bây giờ Viettel với FPT nó thuê rất nhiều người nước ngoài đến Việt Nam làm việc rồi, đúng không? Hiểu không? Chưa biết à? Ôi trời ơi, bây giờ ở trong tập đoàn Viettel cái loại lương 3.000, 5.000 nhiều lắm, đúng không? Thậm chí là các cái ngân hàng mà quản lý người nước ngoài cũng rất nhiều. Một lúc nào đấy các em đi vào những cái resort, thử để ý mà xem quản lý của những cái đấy không phải người Việt Nam.
Mấy năm rồi chưa đi.
Thế thì các bạn phải chuẩn bị thôi. Thế hệ của các thầy là over rồi, nên là các bạn phải chuẩn bị, các bạn tập trung một chút, được không? Feedback lại cái nghe không hiểu nói một cái, tại vì bắt đầu vào những cái nội dung nó khó hơn, nó chemistry nhiều hơn, nó funny ít đi. Thầy cố gắng để làm cho nó fun, nhưng mà nếu mà các em cảm các em không nghe thì nó cũng không có gì là fun cả, đúng không? Một phút nữa đợi các bạn. Có một cái năm 2016 thầy có dạy một cái môn gọi là scientific writing, và sau này năm 3 các bạn học các bạn sao cô Thu Mai Hương dạy. Năm đấy mình dạy mình cũng nói là bạn nào mà không cảm thấy cái môn của mình không cần thiết thì nghỉ ở nhà. Và như mình nói đầu tiên là có 140 thanh niên, và sau khi thầy nói thầy còn 40 thanh niên đi học, không có gì cả. Đến lúc thi trượt một nửa lớp, và còn nửa còn lại thì mình rất là muốn, tại vì hồi đấy mình mới về, mình rất muốn biết là tại sao nó không học. Thế mình thi vấn đáp, mặc dù là một từng đấy người phải thi lại, mà thi vấn đáp nó mất nhiều thời gian như thế nào, đúng không? Cái thi vấn đáp, thực ra cái phần thi mình chả thi cái gì cả, thì mình phải giải thích cho nó là trong cái môn đấy mình đã dạy cái gì, và nếu mà chúng nó học thì chúng nó học cái gì. Và cuối cùng có một ông phát biểu một câu này mình thấy không biết là vui hay buồn, mà như thế này thì em đã đi học. Nói theo gen như là vãi cả ông, đúng không? Okay, so is enough. So let's be back to this lecture. Okay, so come back you please. If you want to listen, you listen. If you don't want to, but please help me. So this lecture, already the fourth lecture of our course, we will talk about ADAM. Okay, so. So here are the 3 main content of the lecture. 2 hours, very simple. First, we will talk about the composition of matter, And then second, we will talk about the concept of atom. So why people call atom? What does it mean atom? How it can represent atom and how the concept of atom can be evaluated in the future. And then we will discuss a little bit the historical movement where the scientists come out with the idea about the structure of atom. Okay? So first, about the composition of matter. If I put this cup here and I look at this, first it will ask several questions. Okay? So let's say if I pick it up, whether it feels soft or hard. Okay? And if inside I give some coffee, hot coffee, the next question is whether I feel it's hot or not. So if I feel it hot, so it means that this material, the matter to make it cup, have a good thermal conductivity, right? It can transfer heat from the solution inside, outside. But if you cannot feel anything, so basically you have a matter which is thermal isolated. That means it cannot transfer the temperature. And if I can feel it hard or soft, that is the sensor, the sensing system on my hand can tell me about that, right? So when I take it one, I can say that it's very soft, but when I pick up this one, it's very hot and hard. Okay? And if I keep it the same volume of liquid, coffee inside, this one I feel lighter, so I do prefer because I get old already. But this guy would prefer this one, very heavy. Okay? So basically all the physical property, soft, hard, temperature conducting, heavy or light, are basically representing the matter and what makes the decision of the physical property. So basically you can say that the two objects are not made of the same matter. This one likely made of the paper and this one made of metal, right? So we'll see that the composition of the two objects will decide the physical property and how we feel these two objects when we touch. The same thing now if you take flame, you burn it. Basically this one you can easily burn, but this is much more difficult or impossible, right? And you know that the burning is one chemical reaction of the matter with oxygen, right? So we can say that because the two matter are made of different material, different components, so they react differently with the same oxygen when you burn. So this also say that they have different chemical property, right? So why the composition of matter is important? Because they decide the behavior of the matter when you put in the environment and how you feel it if you want. That means they will decide the physical property and chemical property. And in the first three lectures, when we talk about matter, the two important emphases are about physical and chemical property, right? If you understand physical and chemical property, basically you understand very well about the matter, but later we talk about the biological property as well. But what we need to understand the composition is based on, because we want to understand how they behave in terms of physical and chemical property, okay? So very long in the past, in China, in Vietnam, people try to understand finally what could be the composition of matter. What are the fundamental elements what constitute all the matter we know. So you know about it, right? Huh? You know about this philosophy, right? Basically, in the Chinese and Vietnamese mindset philosophy, we say that all the matter will be composed of 5 key elements: wood, fire, earth, metal, and water. Okay? So the five elements will constitute all of the matter. That is philosophy. If we try to describe this one in chemical way, you can say that all the matter will have the composition of metal A, water B, wood C, fire D, and earth E. And the value of A, B, C, D, E can vary quite a lot, right? It can vary from 0 to infinite if you want. Okay? So for example, if you have metal, so the value of A will be infinite. And the value of B will be 0, C will be 0, fire will be 0, and earth will be 0. Okay? And if you take a body, like my body, you can say that it will have a component of water for sure, right? A major component of our body made of water. Metal, I'm not very sure whether we will have in our body. Fire, do we have the element fire in our body?
No.
So why make you angry? Why? So people say that when you get angry because the amount of fire in your body get increased somehow, right?
Yes.
Then that's we can say the Eastern philosophy in China and in Vietnam. At the same time, in the Western side, people say that, some philosophers say that, if you take any matter, you can divide it by 2, you divide it by 4, 8, 16, 32, and so on. You keep continuing to divide the matter, any matter, at one moment you will have the unity, the unit that you cannot divide anymore. Right? So they say that matter cannot divide indefinitely. That means you can divide by 2, 4, 8, 16, 32, and so on. But at one moment you cannot cut anymore. You cannot divide anymore. So that moment you have what we call atom. Because in the Greek language, atom means uncut, indivisible. We cannot divide anymore, that means atom. So you say any object with the tool you have that you cannot divide anymore, you cannot cut anymore, we call atom. Right? So let's say when you play Lego, you have different units of Lego, right? And if you own the different subject, so all the unit of Lego that you cannot cut anymore, you cannot divide anymore, you cannot break anymore, that we call the Lego atom. Is it clear? And if you look at this birthday cake, for example, right?
Yes.
You can take this slide and you divide by 2, you have a more friend, you divide by 4, you divide by 8, 16, and so on. So with this, you can be able to divide in very thin layer of cake, right? But the moment the layer of cake you cut is as thin as the line, you cannot divide anymore. Is it clear? Okay? So, if you have the same cake and you pick up different slices, you will have different possibility to divide into different atoms. Is it understandable? So for example, if you take this one, the big one, you cannot divide too much. You divide by 4, it's already difficult. By S, it's impossible. Do you know about this one? Bạn biết cái thanh dao này của ai không?
Con bình thường.
7.
Mà nó không được. Nhớ là của một vị anh hùng nào đấy, em nhớ rõ tên anh hùng đấy. Hơi lâu. Chị biết là của anh hùng tuyệt vời.
Có ai biết không? Của một người Việt Nam.
Thanh giống á. Cái thanh này nó gọi là thanh kia.
Em? Quang Trung á?
Là gì? Em thật sự bộ. Không được.
người tên là Mạc Đăng Dung,
Chịu,
biết không?
chịu,
Ok.
chỉ như cái bóng lưỡi.
No, thực sự không phải. Okay, so that's the life philosophy until the 18th and 19th century. The scientists crossed Dr. Lavoisier. Lavoisier is one French scientist, right? I shared a video about him already. They try to say that, okay, stand here and imagine to say that the matter make an atom, matter cannot divide anymore. It's just imagination. At one moment in England, in UK, the Royal Society, Royal Science Society, under the framework of the King of UK, say that, okay guys, stop trying to discussing, fighting, imagine. We need to do experiment. If we say that the matter make an atom, we should find a way to wait, to see, to touch what we call atom by experiment. And that changed drastically the difference between the Eastern philosophy and Western philosophy. Basically, if you see it as 5 elements constitute all the matter, and the idea saying that any matter you cannot divide infinitely. At one moment you will have a very small building block, and that building block we call atom. So the two philosophies are quite similar if you want, right? So Western side and Eastern side, they have the same concern about the composition of matter, and they all imagine that they should make what we call elemental atom, elemental component. That's philosophy. But then at the 18th and 19th century, in the Eastern side, we keep continue fighting to say that my hypothesis is correct, my imagination is correct, and so on. In the Western side, they say that, okay, imagination is enough. Now we need to go for action. We need to do the measurement. If we say that you take any matter, we cut, at one moment you have an atom, then you take a matter, you cut, and to see what atom you have. Okay? Experimentally. So all those scientists perform the measurement, and they say, and finally they figure out one thing, simple thing. Matter combined with matter in defined quantity, or multiple of the quantity. Do you understand this sentence? Huh? It says, imagine you have this atom, okay? And this atom. So if you take one atom like this, each will combine with one atom, or 2 atoms, or 3 atoms, or 4 atoms in one defined number of atoms. It cannot be 0.1, 0.2, 0.3 atom. It will be not a continuous value. So its difference compared with this. Oh, sorry. Right? So basically, any matter will make a 5 element, and the value, the composition of the element can be varied from 0 to infinity. It can take any value, or we want a little bit fire, a little bit water, a little bit, that means it will be not a defined amount, right? But in the Western side, by doing the measurement, they can make the first conclusion that divides the difference between the philosophy in the Eastern side and the science in the Western side. So they say that matter, that means the component, combined with matter, another component, in a defined quantity, that means one component will combine with one component, 2 components, 3 components, that is well defined, that can be not a little bit. You get what I mean? Clear or not? Tôi thầy xin phép giảng tiếng Việt một chút. Trong cái triết học phương Đông thì mình nói là tất cả mọi thứ ở trên đời này được hình thành từ 5 cái thành phần, đúng không? Kim, mộc, thủy, hỏa, thổ, đúng không? Và chúng ta không thể biết được là một cái vật chất, một cái vật đó, một cái subject đó, một object đó thì có bao nhiêu phần trăm là kim, bao nhiêu phần trăm là thủy, bao nhiêu phần trăm là hỏa. Mình chỉ biết là nó gồm có 5 phần đấy, và có phần nhiều, có phần ít, đúng không? Ví dụ như trong người mình thì mình biết là có bao nhiêu phần trăm là nước, đúng không? Nhưng đấy là cái quantification, cái định lượng của người phương Tây. Còn người phương Đông mình chỉ biết là trong thân người ông có thủy, đúng không? Ông sinh ra chết đi trở về với đất, tức là trong người ông có thổ, đúng không? Còn bao nhiêu thổ thì không nói. Đó. Trong người ông có hỏa, có lúc chẳng hạn sinh viên hơi hơi đấy thôi, đấy là lúc đấy hỏa thần hỏa có muốn nhiều lên bao nhiêu thì không nói, đúng không? Tức là cái triết học phương Đông của mình đang một cách tương đối và không chính xác. Mình nói là có 5 thành phần tạo nên tất cả vật chất, cái đấy là một cái ý tưởng rất là đột phá, đúng không? Thế nhưng mà cái thành phần đấy nó có thể variate từ zero, từ 0 đến vô cùng, và giữa từ cái 0 đến vô cùng nó có thể lấy những bất cứ một cái giá trị nào. Trong khi đó người phương Tây cùng cái thời điểm với người phương Đông cùng nhìn sao thiên trời, cùng nắm thiên văn, đúng không? Thì họ cũng đặt cùng câu hỏi như chúng ta, vậy thì vật chất nó làm từ cái gì? Thì họ nói là gì? Cái ý tưởng đầu tiên của những nhà triết gia Hy Lạp là gì? Vật chất nó được cấu tạo từ những cái phần rất nhỏ, một phần đấy không thể chia tiếp được nữa. Hiểu theo nghĩa là ông cứ lấy cái vật to, vật bé trên rồi thoải mái thì ông cứ chia đôi, cứ phải toán chia đôi ra, đúng không? Mấy ông ICT giỏi chia đôi là cứ chia đôi đến lúc mà không chia được nữa thì cái phần nhỏ nhất đấy là cái phần cấu tạo lên cái vật chất đấy gọi là atom, đúng không? Gọi là nguyên tử. Cái mà các em biết phải nguyên tử có nghĩa là nguyên rồi, không chia được nữa. Trong cái tiếng Hy Lạp là wet, trong cái tiếng wet là atom, có nghĩa là ăn cắt rồi, không thể cắt được nữa, indivisible, không thể chia được nữa, đúng không? Thì về mặt nguyên tắc, người phương Đông và người phương Tây rất gần nhau ở cái chỗ quan niệm đó. Tức là ông lấy tất cả cái vật chất theo quan niệm của người phương Đông thì ông cũng chia ra được đến 5 phần, kim, mộc, thủy, hỏa, thổ, họ không chia được tiếp, đúng không? Thế còn kia thì họ nói một cách trừu tượng hơn, lúc đấy thậm chí còn trừu tượng hơn là cứ vật chất nào thì cũng được cấu tạo vào những phần không chia nhỏ được, gọi là nguyên tử. Tất cả mọi thứ cứ nhìn sao trên trời và cãi nhau như thế cho đến lúc thế kỷ 18, thế kỷ 19 bắt đầu cách mạng công nghiệp xảy ra. Các nhà khoa học cãi nhau chán rồi, tớ đúng cậu sai chán rồi, chẳng có cái gì là cái đừng cả, đúng không? Thì Hiệp hội Khoa học Hoàng gia Anh mới nói hoàn cái này, các sơ, đấy là các ngài thì thế thế stop fighting, làm ơn đo, các ngài mà muốn làm nguyên tử thì làm ơn tìm cách cho tôi biết cái nguyên tử đấy nó cái gì, cầm nắm, sờ nắm hay là đo cân đo đấy nó làm gì. Tức là người ta bắt đầu có một cái ý niệm đầu tiên là thay vì tưởng tượng thì phải chuyển sang thực nghiệm, và cái khoa học thực nghiệm nó bắt đầu ở phương Tây. Đó chính là lý do mà khoa học của phương Tây có phát triển nhanh hơn rất nhiều so với khoa học phương Đông của chúng ta. Phương Đông của chúng ta đến ngày hôm nay vẫn tin vào những cái thứ nó rất là huyền ảo, đúng không? Có thể chúng ta đúng, nhưng mà chúng ta vẫn tin vào những thứ rất là huyền ảo, trong khi người phương Tây tớ không sở được có nghĩa là nó chưa tồn tại, đúng không? Và khi mà người phương Tây đo được rất nhiều thứ rồi, đến lúc họ không đo được nhiều thứ khác thì họ bảo rằng vậy thì có một cái phần compact ở giữa cái mà con người chúng ta biết, có cái phần ngoài cái phần chúng ta biết đấy là phần của Chúa. Và cái cách của người phương Tây họ progress ở trong sai lầm đấy là vì họ biết cái phần của người ta và họ cứ làm cho cái phần của họ nó mở dần ra, cái phần của Chúa càng ngày thu hẹp lại, nó lấy đất của Chúa dần. Ok, thế thì cái kết luận sau khi rất nhiều các cân đong đo đến thì cái kết luận đầu tiên của các nhà khoa học này là gì? Các cái vật chất ấy mà gọi là atom này, unit ấy, nó sẽ kết hợp với nhau ở những cái thành phần cố định. Tức là một ông thì kết hợp với một ông kết hợp với hai ông, một ông kết hợp với ba ông, chứ nó không bao giờ là bất cứ một cái thành phần nào mà mình tăng luôn. Hiểu không? Đến chỗ này hiểu chưa? Hả? Ok? Very simple, right? John Dalton, he published his first paper called New System on Chemical Philosophy. So basically, he said that there are one chemical compound composed of two elements, which is carbon and oxygen. Okay, so you know already there are two elements, carbon and oxygen. And the gas he mentioned, he called carbonic acid because it has property of acid. Basically, if you take this gas, you burst into the solution, it becomes an acid solution. So Dalton at that time, he doesn't know exactly what is the gas, but he called carbonic acid. And he said, and by the measurement, he found out that this carbonic acid is formed of 28 bars mass of carbon and 72 bars of oxygen. That can be gram, milligram, kilogram, no problem. Okay? That means this carbonic acid is composed of 20 equivalent of mass of carbon and 72 equivalent mass of oxygen. At the same time, he have another gas which have also carbon and oxygen in the composition. But when you make the measurement in terms of mass, if you go out that this compound contains 28 bars of carbon and 36 bars of oxygen. Okay? So then he made a conclusion. If you take the same 28 bars of carbon and the reference, 28 bars of carbon I consider as this one. I will see that the first compound, carbonic acid, contains 2 times more oxygen than the second compound. Okay? I don't know the mass will be kg, milligram or not. If I pick up the same amount of mass of carbon, 28 parts, I will see that the first compound, carbonic acid, will have double amount of oxygen compared with the second compound, which we put another gas. Okay? So that makes the first conclusion to say that carbon and oxygen will combine in a defined number, 1, 2, but cannot 1.5, 1.4, 1.6. Is it clear? So, nowadays we know that Dalton called carbonic acid is CO2, and the another gas which is CO. So basically, nowadays we say that yes, Dalton is correct. The amount of oxygen, if you take the same number of carbon in the CO2, will be double compared with the CO. So, you can revise the definition to say that the brick of matter, I mean atom, the unit, the building block of matter combined with brick of matter atom in a defined proportion. I mean 1, 2, 1, 2, 1, 1, 1, 2, 1, 3, but never an indefinite number. Okay? N1 will be a defined proportion. So it supports the atomic theory. Because atomic theory says that we take any matter you divide, at one moment they cannot divide anymore. It says that if you take CO2, you divide, you will have 1 carbon and 2 oxygen, you cannot divide anymore. Right? If you take CO, you will divide, you have 1 carbon and 1 oxygen, you cannot divide anymore. So this measurement support first, the experiment support the philosophy proposed long time ago by the great philosopher, saying that the matter will combine, will be constituted of atom, which is indivisible, untouchable. Okay? So all of the things hide behind 2 laws. The first we call the law of constant composition. That means in a given compound, the relative number and kind of atoms are constant. Water in Hanoi or water in California will contain only 2 atoms, hydrogen and oxygen, and the ratio between hydrogen and oxygen should be 2:1. It will be not change. Even if you break up water here and you put in the any rocket or anything, you find out of the planet, the chemical compound of water will not change. Okay? So that means we call the constant composition. The second law is law of multiple proportion. That means if 2 elements, A and B, combine to form more than 1 compound, the mass of B that can combine with the given mass of A are the ratio of the small whole number. Easy. If you take A and B, you can combine AB, AB2, AB3, AB4. Okay? All the time will be the small number like that, integral number like that. Okay? You cannot generate any AB over 5 or AB over 4. Okay? So that's the meaning. For example, if you take all the oxide of nitrogen, you see that if you pick up 2 nitrogen atom, so this kind of 2 nitrogen will combine with 1 oxygen, 2 nitrogen will combine with 2 oxygen, and 2 nitrogen will combine with 4 oxygen. So you see that all the time the amount of oxygen combined with one given number of nitrogen will be one integral number, small number. Okay? It says that you will not be able to have a compound nitrogen oxygen 1000. It's a big number. Okay? You will not find this compound like this. Okay, so that will be called the multiple proportion. So now, I mean it already. It's implied that if you pick up iron and oxygen, iron will combine with oxygen in a defined proportion, right? That you learn from the law of multiple proportion, right? So it means that iron atom will combine with oxygen atom in a defined proportion. That means if you take 2 atoms of iron, it will combine with 2 oxygen atoms. So in the compound we call FeO. Or 2 atoms of iron will combine with 3 atoms of oxygen in the compound Fe2O3. Is it clear? But it also means iron could not combine with 1 plus X oxygen, when X can accept from 0 to any value. Okay? That's the meaning of the multiple proportion law. Okay? But in our previous slide, previous lecture, we know about this compound, right? Is it correct? In the previous lecture, we talk about this compound. So what's wrong? What's the problem? Where is the problem? Anyone can comment? So, the way I present to you the question, is it understandable? Yes? So, we apply the law of multiple proportion. And we apply this law to the iron oxide. We can say that iron oxide can present only FeO, Fe2O3. But in our previous lecture, we know about this compound. So somehow, by quickly looking at this phenomena, we can say that in the last lecture and this today lecture, you already violates several regulation. Several law. So what is wrong here? Anyone can comment? Huh? So?
Having some of the iron atom as iron 3, it attracts more oxygen, like just in very little quantity. That it doesn't, so it kind of increases the amount of oxygen a little
Yes.
bit, but not,
Yes.
not very much.
Yes. So that we explain and we understand the fundamental of the compound, right? But my question is, this compound is correct, right? This compound is not an energy, it's correct. You have a lot of this compound. But at the same time, you have the law of multiple proportion. So my question is whether the observation of this compound in reality violate the law of multiple proportion? If it's yes, then you need to revise the law. Or you can say that forget because it's not correct anymore. Or you need to revise to make it more acceptable for this exception. Or you can say that no. Nothing violates because some reason behind. We are not talking about the same thing, for example. So that's the way I invite you guys to think about the chemistry. Is it clear? Có cần thầy phải giải thích tiếng Việt không?
Có.
Thầy phải giải thích tiếng Việt nhiều là thầy nói hết lương đi nhá. Tại vì như này, cái luật, cái law of multiple proportion đúng không? Cái quy luật đấy cho mình thấy là gì? Các cái nguyên tố nó combine với nhau bằng những cái tỷ lệ cố định đúng không? 1, 1, 1, 2, 1, 3 vân vân đúng không? Nhưng nó không thể là 1 với 1 cộng x, trong đấy x có thể bằng 0 đến quay lại lại. Đấy là cái quy luật như thế đúng không? Nhưng trong khi đó buổi trước thầy trò mình nói là nó có cái hợp chất nó gọi là FeO 1.02, nó có thể 1.03, 1.04 các loại. Kiểu theo nghĩa một sắt đang combine với 1 cộng với x oxygen, oxy đúng không? Trong khi đó x có thể là cái giá trị mà em muốn. Thế thì câu hỏi của thầy là hôm trước ông bảo ông đúng, hôm nay nó lại có cái lo như thế, có cái luật thế. Thế thì cái hợp chất này nó có vi phạm cái luật kia hay không? Cái quy luật kia nó có bị sai hay không? Nếu câu trả lời là quy luật bị sai thì bố ạ thì phải làm cho nó đúng. Thì đúng phải định nghĩa lại, đúng không? Còn nếu mà không, nó vẫn đúng nhưng mà vấn đề nó ở chỗ khác thì không sao cả, hiểu không? Trong lớp thầy cũng cần nhớ nhiều, cần nghĩ nhiều tí. Và trước khi thầy quy file các em nghĩ thì thầy sẽ giải thích cái vấn đề đó như thế nào. Ok không? Ok, so what's the problem?
Well, I think that the FeO 1.02 that is like a combination a combination of FeO and Fe2O3, right? And that is just something like an average formula within the percentage of each substance in the combination.
Thank you. Other comment? So, the trick here is, in the law of multiple proportion, we are talking about the small molecule, a few atoms, right? Like when we talk about iron O, FeO, that means we talk about 1 atom iron and 1 atom oxygen. And when we talk about Fe2O3, that means 2 portions of the iron combined with 3 portions of oxygen. We talk about 1 molecule of 5 atoms, 2 iron and 3 oxygen. This is basically what we call the condensed matter. That means the matter will contain more than 1,000 atoms. And this, as we mentioned, the formula you have here, that is the average formula. In one location, for example here, you will have exact FeO, and in one location where the iron is oxidized, become iron 3 as we mentioned, so it become iron 2O3. So basically we put everything together with different concentration, different percentage, so we have a different average chemical, that's all. We are not talking about the same thing, so basically the law of multiple proportion is not valid. Okay? So, for instance, with a given amount of carbon, it will combine with m mass of oxygen or 2m mass of oxygen. So we have CO or CO2, it's easy to understand. Water, it will have a 16 gram of oxygen with 2 gram of hydrogen. But if we pick up the A2O2, it will have 2 gram of oxygen, but now combined with 32 gram of oxygen. That means the amount of oxygen in A2O2 will be double the amount of oxygen in the water if you take the same amount of oxygen, hydrogen. Is it clear? Quite easy to understand. But at that time, it's impossible to define the real chemical composition. For example, you say that today we know that it's CO2 and CO, but if you say with a given amount of carbon, the amount of oxygen combined in the case of carbonic acid will be double compared with another gas. So you can see that it can be CH2Y or CXOY, right? So with any value of Y, you still follow exactly the law of multiple proportion. So nowadays we know about CO2 and CO, but at that time Danton can write only CXO2Y and CXOY. Okay? So what we're missing to understand? So we miss the mass or relative mass of the atom. Let's say nowadays we know that hydrogen is 1, oxygen is 8, right? But at that time, nobody knows. So we only know that you have the same portion of the mass of hydrogen with 1 portion or 2 portion mass of the oxygen. So you see that it's quite difficult. And then it's come out with the idea of Avogadro. Avogadro, that means the number of particles in one given amount of matter. Okay? And the idea is that if we pick up the two gases at the same pressure and same temperature, they will react all the time with the same ratio. That means hydrogen and oxygen will all the time react with 2/1 volume ratio. If you keep the same pressure and same temperature. If you have the same volume ratio, that means X volume will have the same number of particles, right? Because you mentioned that if you pick up any chemical compound like hydrogen H2O, all the time you will have 2 atoms of hydrogen with 1 atom of oxygen. Okay? That is number of atoms. But when you make the chemical reaction between A2 and O2 in the gas, you say that you observe that all the time at the same temperature and same pressure, 2 volumes of hydrogen will react with 1 volume of oxygen, right? So it means it doesn't matter hydrogen and oxygen, they are different, but in 1 volume of hydrogen and 1 volume of oxygen at the same pressure and temperature, they will contain the same number of particles. Is it clear? Huh? So that starts the idea with Avogadro number. That means in any given amount of mass, you will have the same number of the particles if you keep the same pressure and same temperature. Of course, when you change the pressure and temperature, you change. Because later you have M equal to BV/RT, right? Okay. So we are almost there to understand the chemical composition of one very simple compound like water. You have the same amount of hydrogen, we have the same particle with the same amount of oxygen, and we know that each time the volume of hydrogen react with the double volume of oxygen. So nowadays we say that H2O, right? But it can be H4O2. It can be H6O3, right? So you see that you take the ratio volume of hydrogen and oxygen, you cannot say it's 2/1 like today. It can be 4:2, 6:3, 8:4. So how people also come out with the idea that no, it's not H4O2, H6O3, but H2O. You need to define the mass of one molecule, right? Because the mass of one molecule H2O will be half of the H4O2, right? So if you know the mass of one molecule, then you could be able to define exact number, not the relative number. So, to summary, it's quite quick. X element is composed of x times small particle called atom. That you cannot divide anymore. That indivisible. And then X element, all atoms are given in element are identical, except for the isotope we will see later. Atoms are not changed in the chemical reaction. Okay? During the chemical reaction, what change will be the electrons surround the atom. We will see later, but the atom itself will not change. That means if you pick up water and you make the water electrolysis, you will have hydrogen and oxygen. So the atom of hydrogen in water and the hydrogen atom in hydrogen will be the same. Okay? It will not change. The camel are formed when atoms of more than one element combine. That we learned from the last lecture already. A given camel always have the same relative number and kind of atom. H2O should be H2O forever. Wherever you put in Vietnam or you put in the US will be the same. Okay? Now, we say that all the matter will combine indivisible matter we call atom. So what would be the size of atom? How big one atom is? Can we touch, can we see the atom? So in the chemistry you learn in the class 10, the atomic structure you learn in the grade 10, right? You learn that basically atom is extremely small, you cannot see it. Is it correct? Say that the atom is extremely small, you cannot see it. So how is small? Basically, one atom have a diameter between 10 power 10 minus 10 meter. So basically, it's about 100 to 500 picometer. And 1 picometer equal to 10 power minus 12 meter. Okay? So it's about 2 angstrom for the K of chlorine. The atom is 2 angstrom. Okay? How is small? Let's say if you pick up and the hair, the diameter of the hairs is about 5,000 nanometer. Okay? Okay? 5,000 nanometer is about 50,000 angstrom. So that means if you take the diameter and divide by 50,000 times, you will see the size of one atom. So with the naked eye, you cannot see it. But then, nowadays, I guess the textbook should mention differently. We cannot see with our eye, but we can take a photo of the atom, even they are extremely small. So for example, you see here the image of the copper atom. So a dot here is one copper atom. Okay? You can even see the area normally occupied by the copper atom, but then there are no atom standing. So the copper atom is about 1.3 angstrom in the diameter size. Even it's extremely small, but we can see it, we can take a photo of it. How we can take a photo of the atom? We discussed already, right? In the previous lecture. If you want to take a photo of the atom, basically you pick up electron. Electron is much smaller than the atom. You send the electron to the atom. Let's say if you have a beam electron like this, right? You send. So when it sees copper atom, the electron will be back. So you detect it. But when the electron flow and is not hit the copper atom, then the electron will go through. You cannot detect it anymore. You see what I mean? So let's say if you send electron and here you pick up a detector to count the electron back. So when you send electron, if it hits the copper, electron will be back. So this point we know it belongs to the copper. And then you move to the other position, you send, the electron will not be back. So you see that this point will not belong to the copper. You repeat this case, so you collect all the image where the electron hits. So basically you have the side of the copper. Right? So that's the way people pick up the photo of copper atom. Is it clear? So, It's not only in the textbook. In my research lab, we can pick up the picture of the atom. So here you have a molybdenum sulfide, and you see that all the molybdenum stand like this with dot. They will stand in a triangle with the distance between the two atoms 2.7 angstrom, very small. We can make it. This photo we can take. We did already 7 years ago. The problem is that it's extremely expensive. One experiment like this in Japan, we need to pay $1,000. One experiment. When you put sample inside to take a photo, 1,000 per one photo. Very nice. Now, you understand the concept? Let's work on this question. To clearly visualize the atom, to take a good photo of the copper atom, for example, this one, we should conduct the measurement. We should collect the photo under following condition. First, room temperature. Second, high temperature. That means you try to heat up the copper to get almost the melting point. Or you pick up the low temperature, for example, almost 0 Kelvin. In weak condition, you will have a better image and Y. A, B, C. Which could be the correct answer?
A.
A, why?
Okay, so this picture of the Angela Coopers look in the microscope. So I think the best temperature should be the room temperature, because if the cooper is higher, so it's going to come down or break. It's may break the microscope. But if the low temperature, so on the surface of the atom may have a snow on it, so we cannot take a picture.
Okay. Thank you. So A. Who have different answer?
I think it's C, because the lower the temperature, the more the atom will be stood still. And you want to take a picture of something that stood still rather than something moving.
Okay, thank you.
Thì nó
Any other idea? The last comment.
nguyên tử do chút electron.
I think it's B, because when it came to the melting point, the distance the atom became larger and you can take a clear picture with individual atoms.
Okay, thank you. So basically you have A, B, and C, right? So the correct answer is C. The reason is like, hey, guy, you try to take a photo and your friend like that. So you cannot pick up, right? You cannot pick up a good photo if the guy moving all the time. Okay? So the thing is that you send the electron and this guy will moving like this. Oof, sorry. Oh, this one, huh? This will moving like this. Okay? And this moving will depend on the temperature. Higher temperature, the movement will be faster. So at 0 Kelvin, if you have 0 Kelvin, this temperature, 0 Kelvin absolute, it will have no movement. The guy will stand like this. So you can pick up the photo easily. Okay? But of course, you can hardly to reach absolute 0 Kelvin, so you make likely a minus 10 Kelvin. Okay? So if you see that the thing is that sorry, 10 Kelvin minus 10 Kelvin, 10 Kelvin. Okay, so the lower temperature will be better for the measurement. About his comment, he is thinking about taking up the picture with the optical microscope, right? Now, it's very interesting. Can you comment why we should take an electron microscope? That means the beam should be electron, but not an optical microscope to take the picture of the atom. In other words, can we pick up the optical microscope that you have already experienced with your high school practical training, right?
Yes.
No.
Can we use the optical microscope to observe the atom? No, why? But why cannot increase the visualization with the optical photon?
I think it would cost more money to do that rather than.
No.
No.
Yes?
Em chưa tạo một cái review bao giờ.
Yes. So the optical microscope, basically you use a visible light, right? You send the visible light to the sample and you observe the scattering or transferring or transmission and so on, right? So the visible light ranges from 400 nanometer to 800 nanometer, the wavelength. So it looks like you want to observe this atom, but you pick up, this probe. Okay? So you cannot see anything, right? All the visible light you send, they will be scattered back. So you see only the black picture, right? Because the wavelength is too long compared with the atom. So that's why when you have this object, you need to find out the probe, which have a smaller size compared with the object. So if you want to take the neutron side, the object you send to should have smaller size than neutron. So that's basically electron. What could be the size of electron? We say that it's smaller than atom, right? But what could be the size of one electron? In other words, is electron a matter?
No.
Photon is not matter, right? That time we discussed already. How about electron? Is electron a matter? Yes or no? Huh? The matter is something have the mass and occupy space. Right? So, does electron occupy space? Yes. If not, how can you have orbital? Right? It occupies the space. Do you know the mass of electron?
Yes.
Yes, we know it's not zero. Right? So it's a matter. But what could be the size of electron? It occupies the volume for sure. Huh? But the volume is occupied and the size of this is not the same thing. You agree with me? Huh? Các bạn có hai cậu sinh viên, một cậu béo hơn cậu khác, nhưng cái cậu béo nó cứ ngồi một chỗ thì nó occupy cái volume rất là nhỏ, đúng không? Cái cậu gầy thì nó chạy khắp phòng thì nó occupy cả cái phòng này. Okay? So the volume the electron occupy and the size of electron are not identical. They are not identical concept. So what would be the size of electron? Huh? Smaller than neutron, sure. Because otherwise you cannot detect neutron. Huh? What could be the size of electron? Đi học toán các thầy bao giờ hỏi các em là một điểm nó to hay bé? một điểm kích thước bao nhiêu biết không? Một điểm là cậu sinh viên nữa là một điểm bao nhiêu, một điểm kích thước bao nhiêu là phụ thuộc vào biên phân là thầy ấn nó như nào. No. So that's funny, but electrons have no dimension. It's like point. Okay? So the point have no dimension. So basically, you have not only you cannot say about the size of electron, but the electron occupy the whole. Such a crazy thing, right? Okay. So you see, with this kind of imaging, we can be able not only to see the exact position of atom, but you can see in the picture where the position normally should occupy that atom, but now it's become vacancy. That means it become defect. So last time we mentioned about the iron oxide, right? We say that some iron will be oxidized to become iron 3. That means some other need to go out as well, right? Because you need to balance the charge. Okay? Let's say if you have a 3 iron 2 plus and 2 become 3 plus, that means you have already equal charge. That means the first one should go out. Okay? So that is your imagination. But nowadays, with this kind of equipment, you can see where the position iron normally should stand there, but because the guy beside oxidized to be 3 plus, this guy go up. Okay? So you see here, normally it's occupied by one atom, and one atom, and now it's become empty. Okay? And now you see that if you have this object, okay? Imagine that in the structure of this object, all the structures are perfect. That means they are in very good order. You will hardly break it. But if some position here normally occupied by some guy, but now it's become empty because they go out. So you have some empty space in here, so you can break it easily, right? Right? So look like if you have a perfect structure, you have an excellent teamwork. Okay? But then some defect mean, so this guy worked very hard, he are excellent, I don't need to do anything, I decide to quit. Okay? And when you decide to quit, your team become easily to break that. Okay? Is it understand? If then, it means if you want to make a chemical compound which are stable, you should try to find a way to make it perfect. Good teamwork. Very well ordered. But if you want to make something active, that means react very fast with oxygen, easy to burn, please do not make it perfect. Perfect, stable, means not active. If you want to make it active, you should try to find a way to make it very defective. A lot of defect. Okay? So it also say a good student all the time sitting there listening from is good boy, stable, but not creative. And if you guys, some guy like you have a lot of creative guy here, right? You don't listen from. You forget all the order, nothing interesting. Because you are thinking about the other thing. So basically you are more active and hopefully you are more creative. But that's also the same philosophy for the chemical compound. So if you want to make a material, a metal, to again the corrosion, again the force, again the fighting, then you should make a structure with a perfect order of the atom. All the atoms need to put in the perfect order. But if you make something very active, like you want to burn it quickly, you want to dissolve it quickly, then you find a way to make order with a lot of defect. Okay? Is it clear? Now, then it is clear, think about this one. Considering this material, so the structure you have here, with atomic effect, the law of of multiple proportion is no longer correct, still applicable, applicable or not depending on the type of defect, not applicable for the condensed marker in general. So the answer we discussed already, right? We are talking about a marker containing 1,000 and 1,000 atoms. So the law of multiple proportion will not applicable anymore, because the law of multiple proportion applicable only for small compound with limit given number of the atom, right? It's quite easy. Now another question. Given that I explained to you, certain chemical property of a component will depend on the structure defect. Let's say I mentioned, more defect you have, become more active, less defect you have, become more stable, right? The question is that, which the following strategy can be adopted to create high population of structure defect? That means, I want to have a very creative guy, very active guy. So, by the logical thinking, I want to create a lot of defect. So, the four strategy, which one can help me to create more defect? For example, the case of sodium chloride. The first one, I pick up sodium chloride, maybe perfect already or less defect. I dissolve in the solution in water, and then I slowly recrystallize. I dissolve it, become liquid. I recrystallize by letting the water vapor slowly evaporate. Okay? The second strategy is that I dissolve sodium chloride in water, and then I quickly crystallize. For example, I pick up the solution, I put in the fridge. Okay? The third one is that I apply a high pressure to this crystal. I pick up a crystal, I apply high pressure to press it, whether I can have higher population of the defect. The last one is that I dissolve in solution of water, and during the crystallization, I put calcium chloride inside. So which of the strategy, and I explain to you and you think about this, which of these strategy can give you a material sodium chloride with higher population defect? Am I clear in my question? Yes? So can you think on that? 2 minutes.
Hỏi là có chúng nó tốt hơn hay là không nữa?
So, okay, I try to be clear. Let's say you start to have sodium chloride with certain amount of defect already, right? It can be zero, it can be quite good population. But I'm not happy. I want to make more population of defect. Okay? So here are the 4 strategies. I start from sodium chloride. Which one can offer me more population of defect? That's my question. Sao, có hiểu không? Ok. Thầy sợ nhất là nó không hiểu câu hỏi của mình. So, any idea? Any comment? Huh?
Teacher, I have an idea.
Which one?
D.
B?
D. D.
B?
D.
D?
Yeah, D.
D? B, okay. B, D maybe, right? Okay. Who have the same answer like B and D? Okay. Thank you. Why? Why you come out with the idea?
I think I like to. The answer I like if you leave the solution to slowly evaporate, the water will have time to get out of the solution, so it leaves it crystallized pretty pure, and I think that sounds less effect. B, when you quickly crystallize it, at a time the crystallization is offering, the more water can have time to. That's it.
Okay.
About C, I have learned in high school that crystallization, the form of crystalline ice crystals are not actually really stable in high pressure. But B, I'm not sure about B because I don't actually remember the level of solution of salt and calcium chloride. If the calcium chloride will dissolve more than 7, it depends on which one of them will crystallize first when you decrease the temperature.
If they crystallize at the same time.
Then I think you will have more defect, I guess.
Thank you.
Thank you. So before talking about the correct answer, I would like to explain to you the concept. I say that, okay, the good structure I want, the perfect structure I want is that these guys sit here, these guys sit here, these guys sit here, okay? I pick up a picture and I say that this pattern you sit in this position are the pattern I want, the crystal I want, right? And I say that, okay, you guys stand up, go up. So you have the empty plate, right? And I say that now I want you guys come back to sit in the exact position you have now. There's two scenarios. I say that you have only 1 minute. Quickly, because we start the examination now. Then maybe the first guy will have time to occupy the first position. Maybe the other guy will need time to organize and pick up the right position. For example, this guy, normally he sits there, okay? So in the good order, this guy should come first, sit first, and then this guy fill in this position, right? But because you have only 1 minute, so this guy will not care. He sit here. So he will mask the position of this guy. So this guy will say, hey, you will not care. I don't care. Now is the time for examination. So this guy will sit anywhere, right? Because the examination will come. So this guy, probably he will sit there. So normally he should sit there for the correct pattern. And he sit there. So basically he create already one defect. The same exercise. But I say that, okay guy, please go out. You will have 1 hour to sit correctly. So if guy will go. I thought, oh, this is my place. So this item, all of the guy will have a lot of time to find in a good position. If this guy already come to sit here, but still 1 hour, the guy will have, okay, stand up, I will pick up this position. You see? So the item will do the same thing, like you guys. So if you dissolve, that means all the guys stand up, go out, and then you give a very short period of time. The one will quickly fit in the position, but the probability to fit wrong position is very high. So you create more defect. Okay? And then if you take the same exercise but you give higher time, longer time, that means the rate of crystallization will be slower. Then the guy will have time to choose correctly the position normally he or she should occupy. So if you do like the first one, you slowly evaporate water, like you say, okay, 1 hour, I will have 2 hours for you guys, do whatever you want. Then basically they will have a perfect structure with very low population of defect. In the second case, you have only 1 second. So they will try to occupy what they can. So they will get a lot of defect in the structure. That also reason when you do the practical chemistry in the second semester for those studying biology, chemistry, physics, when you do the recrystallization, if you cool down quickly the temperature, you have a quick precipitate from the particle, from the solid, but all the particles will be small. The reason is that because it's quick, so this guy occupies this position, this guy will soon occupy this position. So basically only one small area, the pattern exactly what I want. Okay? So I say that all the guys sit wrongly in the pattern, you go out, you don't take the examination anymore. So the amount of the guy, the number of the guy will take the examination will be decreased. So that make the perfect, because when you have too much defect, like when you build the high building, more defect you have, the building will collapse, right? So that you cannot build a big crystal with more defect. So the B will be one excellent thing. C, when you apply high pressure to say that, okay guys, here is one defect, there one vacancy. Here you go. I push like this. So basically, this guy, if I push enough energy, this guy will jump to occupy the empty seat. So we will reduce the population of vacancy, right? So that's also, nowadays, there one field of research we call the high pressure science, high pressure material. That means, basically we create a material, matter that a lot of effect you don't get. But then you press a high pressure to have a perfect structure. That's also why, if you want to have a diamond, because diamond have a structure with very less defect, you need to apply a high pressure. Okay? It also say, if you want 20 over 20, you need to work hard under the pressure. So C will be not a good case because it will have less defect. How about D? Okay? I will say, okay, imagine sodium chloride. Sodium is boy, chloride is girl. So I want a pattern boy, girl, boy, girl, boy, girl. Okay? A good order like this. But then I have a twin, 2 guys, who have 2 positive charge. They are 2 boys, right? And they prefer that my parents say anywhere over the world, including in the class, we should sit beside each other. Can you separate? Put a lady in between? No. My parents say no. To be or not to be, whether we sit here or we be back home. Okay. You pick up 2 positions. So in that case, the next, normally, you have 2 positive charge, and in between you have negative charge, right? You have 2 boys, in between you have lady. But because this guy is twin, and they have 2 positive charge, they occupy already the position normally occupied by 1 positive and 1 negative. So the thing is that the next normally positive become negative, right? So if you continue like that, at least 1 lady will not have place, and she will need to go home. Okay? And then by the same way, because normally the 2 places occupied by 2 boys, right? Now it become twin already, so 1 boy, normally not twin, needs also to go home. So you get more defect by this way. Is it clear? Huh? You see, so the chemistry by the explanation of form is not difficult to understand, right? If you want to understand. Okay, so now we talk about the discovery of atomic structure. What is atomic structure? So now, you know about this, right? Everybody know about this. Atom will contain an electron, runs around, you have a nucleus, make a proton and neutron. So, but how people can recognize that the atom is made of electron and make a proton, neutron, and nucleus. And how the electron runs around and how people say that the nucleus is very small but heavy. Okay? So if you look in the history of the discovery of atom, first at the time of Dalton, Democritus, people say that atom is something you cannot divide, right? You cannot divide anymore, so that we call atom. We don't know exactly what to be the structure. And then Thomson came out in the 19th century, we say that this kind of structure, you have a red dot with an electron, negative charge, and you have a neutron, which is positive charge, a big one, positive. And then later on, Rutherford, the student of Thomson, saying that no, Professor, you are wrong. The nucleon is much smaller, positive, heavy, like you say, but not big, like you say, it's small. And then after that, Bohr, we say that actually electron will run in the substance orbit from the nucleus. Okay? And very recently we have a complete, much more better understanding about the atomic structure. We say that actually the electron is not running in the given orbit like that, but they run randomly in what we call orbital. Okay? So we call the cloud of electron, not orbit of electron. So let's go to see the key experiment helping to discover the electron. First, the key message is that there are many electrons in matter and they are easily to be attracted. That means any matter on the surface you have electron and you can easily to attract the electron from the matter. Okay? So what could be the experiment? You know about the cathode ray experiment, right? Thomson experiment. Basically, you have an anode made of this one, anode made of gold foil, very thin gold layer. And then you apply high voltage. You see that the electron will attract from gold and flow directly to hit the luminescence. So when the electron flow through the tube with the vacuum, go to this luminescence, it will brighten up. So each time you see the bright dot, you say that there one electron flow down. Okay? So when you apply, when you put the magnet, the pathway of electron will be deformed. So saying that the magnet can control the pathway of electron, it means the electron will be not neutral in charge. It will have a negative charge. Later, you know. So the same thing you do here. If you have a high voltage applied from the anode and the cathode, the electron will flow directly, and you see that the luminescence will rise linearly like this. And when you apply a magnet, the electron curve will change. So here are the first conclusion. The magnetic and electric field can change the cathode ray pathway, can curve the transformation way, the direction of the electron. I will not go very detail. So this you can have at home. So now we know about the electron attract from the metal which are negative charge. Okay, and then after that, Millikan try to weight the mass of electron and come out with the electron mass this value. H time is small, right? It's almost zero if you want. So the message you learn is that on the metal you have a lot of electrons and it can be easily to attract out. So if you take a metal, you heat up the electron can flow from the surface of the metal. So in that case, you have electronic effect. That means you heat up the metal, the electron will flow to make electric current. Okay? You can send also the photon to the metal and attract the electron from the metal surface. So imagine that you have a metal surface here. You take radiant energy, that means from a photon, hit the metal, the electron will flow out, and then you can collect it in the positive electron, right? So all of those things are very well established. So in this case, we call the photoelectric effect. That means you have a photon, you send to the metal, you attract the electron, so we have electron current out. Okay? Imagine the following. Before, people know very well that gold metal, right, have a bright color, yellow color, right? But then nowadays, with the nanotechnology, people understand that you can change the color of gold metal from the purple, brown, pink, to even yellow, green color. So you can make golden particle with different color. So what could be the reason? The key is that, imagine you have the particle of gold. On the surface you have a lot of electrons, right? Okay? So basically electron will not stand. It will move like this. Okay? So if one electron moves by this way, another electron moves by the other way, then nothing happens. But imagine that somehow you make all electrons move in one direction and then back in the same direction. So we have the phenomenon we call the resonance. Okay? So depending on the particle size, depending on the size of this object, gold object, the wavelength of the photon that make this resonant movement in one direction will change. So the smaller particle will have smaller size for this resonance, and when you change to the bigger, you change the resonant photon. So when the particle absorbs the photon to make this resonance, so it's so the color you have here, what we call the plasmonic effect. So I invite you guys to have self-study on this. You know about this guy, Michael Faraday? Mike Faraday. Có ai biết ông Faraday không?
Cái thằng số Faraday với cả cái nguyên lý lồng Faraday.
Có biết câu chuyện về thầy đi xin việc như nào không? Thầy của Faraday thì có biết là ai không? Thế người tìm ra oxy là ai biết không? Ok, thôi thầy kể luôn. Thầy của Faraday là một viện sĩ viện hàn lâm khoa học Anh tên là Davies, hoặc là Sir Davies. Thế thì thông thường thì hồi đấy các trường đại học nó chưa có các cái khóa học và chưa có các cái bằng cấp, nó chưa có tuyển sinh gì đâu. Thì Davies thường đến hội hóa học Hoàng gia Anh và đọc các bài giảng, và có một cậu sinh viên rất là chăm chỉ ngồi ghi chép, rất là nhiệt tình, rất cẩn thận các bài giảng của Davies và không thiếu một bài nào. Đến một ngày thì cậu ấy đến gặp Davies nói là: thưa thầy, tôi muốn xin một việc ở trong phòng thí nghiệm của thầy để học. Thì Davies cũng rất là lịch sự với người Anh, và gentleman, không từ chối, để tớ sẽ xem xét. Thế xong về mới nói với cả đồng nghiệp trong khoa là có một cái cậu nó cho tớ xem cái quyển sách của nó học, nó chép bài của tớ rất là sạch sẽ, rất đẹp, và nó có vẻ rất là thông minh, và muốn xin làm việc ở phòng tớ. Nhưng mà tớ chả biết cho nó làm việc gì bây giờ. Thế là chắc ông bạn cũng đùa cho đi sửa dụng cụ thuyết minh. Thế là Davies mới mời Faraday đến nói: bây giờ tớ chỉ có một việc cho cậu làm trong phòng thí nghiệm của tớ, nghĩa là đi rửa dụng cụ thuyết minh. Thì Faraday nhận ngay lập tức. Và bắt đầu từ cái công việc sửa thủy tinh đấy, và các em có một Faraday thiên tài đúng không? Điện hóa cũng là hàm số Faraday đúng không? Lồng Faraday đúng không? Và bây giờ mọi người ở đây có ai là học khoa vật liệu material science không? Bây giờ mọi người nói nhiều đến nanotechnology, nhưng các em có nhìn thấy cái ảnh kia không? Đấy là cái dung dịch vàng, cái dung dịch từ các nanoparticle vàng mà do hai cơn Faraday chế tạo ra và để lưu lại ở trong thư viện, trong bảo tàng của Hội Khoa học Hoàng gia này. Để cho nghĩa ông là một người đi trước con cháu chúng ta cả trăm năm, hơn trăm năm. Thế và sau này khi mà Ham Davy được người ta phỏng vấn, cụ Davy thì cũng có hai câu nổi tiếng. Câu thứ nhất của cụ là một nhà báo hỏi là chất này có độc không thầy, chất này có độc không thầy? Thì cụ bực quá cụ nói trên đời này chẳng có quái gì không độc, chỉ mỗi oxy là không độc thôi. Đấy là câu nổi tiếng nhất đấy. Tất cả mọi chemical compound đều độc. Quan trọng là nó cái dose, cái hàm lượng của nó như nào đúng không? Thì trừ mỗi oxy. Cái câu nói thứ hai mà rất là nổi tiếng đấy là khi người ta hỏi là sau khi mà cụ chuẩn bị về hưu ấy, thì một phóng viên người ta hỏi là thế trong cuộc đời làm việc mấy chục năm của cụ ấy, thì cái phát minh nào là phát minh vĩ đại nhất? Thì cụ nói là cái phát minh vĩ đại nhất mà tôi thể lại trong khoa học là phát minh ra Faraday. Và sau này các em thấy là cái slide về data structure để được các em thấy là cái người đầu tiên làm cái thí nghiệm cathode ray ấy là Thomson. Người hoàn thiện phần tiếp theo Thomson tìm ra electron và đưa ra cái mô hình đây đầu tiên. Người tiếp theo hoàn thiện cái mô hình đấy là Rutherford. Rutherford là sinh viên của Thomson. Thầy bảo là một thí nghiệm cậu chắc là cũng active, tôi không thích làm thế, tôi làm khác, và cậu phát hiện ra một cái structure mà correct cái structure của Thomson. Và sau này người mà tìm ra photon để hoàn thiện phần nữa cái structure của atom là Chadwick. Chadwick là đệ tử của Rutherford. Ok, thành ra là nếu mà các em quyết định làm khoa học ấy, thì tìm thầy mà học. Ok, việc học thầy không, thầy chẳng discover là cái gì đâu. Okay, so back to this firework, you know very well, right? In this firework you have different color. So maybe you ask yourself how you can have this magnificent color, how you can have this beautiful color. Okay, so if you want, this is how firework operate. So you have this area, you have energy to combust to make the rocket, the fire go up, and then in the fourth place, you will have some iron. When the iron burns, it will emit the light that you see the color. Okay? So you can see here, for example, for the energy center, you just burn the potassium nitrate with the carbon and sulfur, and then you have energy that will pick up the rocket up, and then this energy also activates the sodium, potassium, barium, calcium, and chromium inside the fourth layer, and then it will emit. For example, when you have a potassium, you will emit the violet color, so you will see the violet color. If you have a chromium, you will see the red color. Okay? So this one I keep no problem. So here describe how basically the color will separate during this firework operation, and we're not going to detail. And that's only for fun. But in the science technology every day, because of this emission of the color, you can detect different metal in the environment. So I invite you guys to work at home. So nowadays, if you want to make a summary about electron have a point-like particle character that means no dimension. It's like a point. It is elementary particle, that means you cannot divide anymore for the moment. It has a negative charge. It's very light with a mass less 1,800 times less than 1 atom of hydrogen. And electrons are numerous. You have a lot of electrons in any matter, but their contribution to the total mass is very small. So let's say if you pick up 1 kg of iron, you have only 26 electrons per atom. So in total, you have in 1 kg of iron, you have only 550 milligram of the electron. This is very small, right? So now, how about the nuclei? Because any matter are neutral in charge, right? So if you have an electron which is negative charge, then you have something else which have positive charge with the same number of charge. You have a X negative charge electron, then you should have an X positive charge or something else. And you see that you have an atom which have the mass. And you know that the electron is extremely light. So that means the positive charge content, the remaining mass should be extremely heavy, right? The main mass of the atom will be in the positive part of the atom. So now if you make a logical thinking, you say that electron very small, light, which have almost no mass, then the remaining mass should be big, heavy, right? So you have a kind of linear operation between the mass and the size, right? If you say that electron and nuclei, the positive part, will have the same mass density, then because electron is very light, then the remaining part positive should be heavy. The electron is very small, then the remaining part should be very big, right? So because of this logical thinking, so Thomson proposed this kind of structure, saying that the electron is very small, it's like dot like this, and it's then surrounded with big positive charge. We call the nuclei, right? So now imagine, if this guy is positive, and if I have a particle, it's also positive, right? I take like this. This particle will be back, okay? And then, if I go here, I do the same thing, it will be back. If I turn around like this, it looks like this. Yeah. Okay? If I do like this, it will be back. Like this, it will be back. Okay? So I turn around, I can map the size of this particle, right? Of this positive charge. Is it correct? So, after this proposition, Thomson talked to his student Rutherford, saying that, hey guy, there one group in France, Marie Curie, Becquerel, they discover the alpha particle. The alpha particle is positive charge. So you will pick up the alpha particle, you put like this. You run around and you try to show me what could be the size of the brown part of the particle. Okay? Thomson said, if I do by this way, I do several experiments, right? I put here, I run, I put another one, right? So instead of doing that, Thomson is very lazy guy, very creative, saying that, okay, my professor said, this is the nuclei, positive charge. I will pick up the alpha particle with the positive charge from Marie Curie and Becquerel. I will put like this. I move to the other position. I put like this, it will be back. Put like this, it will be back. Put it like back. It will be like back, right? So he said that I will do experiment one at a time. I will put my object here, and surround. I will make the luminescent layer. So if I fill this way, the luminescent will be back, and then I change, so automatically I will map the thing. You understand what I mean? So here is Rutherford experiment. So instead of making like Thomson recommend, I pick up this one and move like this. Okay? I keep this one. And I make the curve luminescent curve like this one. So what I expect? I expect that if it's correct like Thomson model, I put the alpha here, I will not see anything. I see only the alpha back in the same direction. Okay? But actually, the real observation of Rutherford is that when it falls from the alpha rays to the particle, to the middle, you see all the particles will hit this direction, but not scattering other direction. So it means that if I pick up the alpha ray, the particle here, I threw all of the particles will go through. So that means this nuclei is not big like that. It's very small. So all of the time I threw the alpha particle, it will go through the system, but not hit the particle, positive charge, and be back again. So with this experiment, Rutherford said, okay, here, professor, here is correct structure of the atom. You have the electrons around, you have nuclei with positive charge, but very small, not big like you imagine. So when I hit the alpha particle, most of the time it goes through. And only few you will see hitting the particle in the back. So you see that this experiment showing finally the particle, the nuclei inside positive charge, heavy, but extremely small volume. So we will say that electron negative, very light, but occupy the whole volume of the atom. The nuclei heavy, positive, but it's almost nothing in the core of the atom. Okay? So here are some of the summaries I mentioned. Later on, Chadwick, I mentioned, the student of Rutherford discovered the neutron and complete the structure. So here are the summaries. Nuclei are very small and heavy, make a proton and neutron, so make nucleon in general. The particles are not elementary, so they can divide and they can divide further what we call a quark. And they are not point line, they have a volume, they have a precise size. Their mass are very heavy, 1,800 times heavier than the electron. Okay? So here are the summary of the proton, neutron. Okay, so here some final information. You have the atom made of electron, nucleon. So in nucleon, neutron, you have proton and neutron. Okay. So we talk about isotope. That means you can have number of charge equal to number of the proton, right? Because number of charge equal to number of proton equal to number of electron. But number of mass is total number of nucleon. That means the proton and neutron. So number of proton will be not changed if you have the same element. The number of neutron will be different. So when you have the same number of proton, when you have a different number of neutron, you have different atom, nucleon, what we call the isotope. Okay. So for example, if you have carbon 12, you have 6 proton and 6 neutron. But if you have a carbon 14, that means you have 6 proton and 8 neutron. Okay. So the different isotopes will have different content in the nature, so that's why the average mass of the atom will be different. So I will finish at the last slide, which is important. How the isotopes are important. Let's say in real life. Now people are trying to convert CO2, which is greenhouse gas, into formic acid, CO, or other compounds that can be used later like fuel, right? To replace the gasoline. And nowadays people develop this kind of material we call the graphitic carbon nitride. So you see that it looks like graphite, so it looks like the benzene light, but instead of having carbon, you have nitrogen, carbon, nitrogen, carbon, nitrogen. Okay, so you change the structure. And some people claim that this material is good one for the reduction of CO2 into CO, into formic acid. Okay? The idea is that you put CO2 inside with this photocatalyst inside the visible light, sunlight, you will have the product with CO formic acid. One guy, who I know, doing an experiment like following. He take this material and put a mixture, not a pure CO2, but a mixture of CO2 12 isotope and 10% of CO2 14 isotope. And the product he got is CO with the carbon 12 isotope and formic acid with the carbon 12 isotope. So the question is that if you look at this information, evidence, can we conclude that CO and formic acid are produced from the CO2 reduction? Is it clear? Do you get my question? Yes. So what could be answered? Yes or no? No, why? Yes, why? Any idea? Huh? Yes or no? So, we don't have time, we are one time. So basically, the answer is no. Right? Because it is made of CO2 reduction, that means you could expect to have CO product with the carbon 14. It's 10%. And you also expect the formic acid with the carbon 14. Here you have only carbon 12, that means it's coming from something else, not CO2. So the next question will be, what could be something else? Where the carbon with the carbon 12 isotope are produced, if they are not from the CO2 reduction? Because you have the law of the conservation of matter, right? The matter should not be generated, it should be transformed from something else, right? So where can you find this CO and formic acid if not from the CO2 reduction? We agree that this could not be from the CO2 reduction, right? If it comes from CO2 reduction, you have a mixture of 10% of carbon 14, so you should have a mixture of product with the carbon 14. Here you don't have. So it's not from the CO2 reduction, but come from which source? Huh? So basically it comes from the carbon. You start from the graphitic carbon nitride, you produce what you thought come from CO2 reduction, but not the case. You destroy your material to produce CO and formic acid. So what I want to share here is this. The isotopes are extremely important for a lot of applications in the biology and in chemistry. This kind of experiment we call the labeling experiment. Okay? So it's time off. So to prepare for the next section, thank you, and we stop here. We see you next week. Thank you.
Bạn ơi, lấy hộp về cục tẩy được không? Ôi giời ơi. Bạn ơi, mình thấy bạn có quay video của ngày hôm nay không? Bạn có thể cho mình xin cái video được không? Video hôm nay hay là video bạn